Yes.
Okay.
Thank you, Bob. Thank you, Con, for the invitation. Let me share the screen. Does it work?
Yes. Okay.
Yes.
Yeah.
Okay. Okay, so today I want to talk about dissolution dynamic nuclear polarization, and so the title mentions this inexhaustible spring of hyperpolarization. So the thing is, with three questions, I really want to show you how today we think that we may be able to transform dissolution DNP from a method that is today single shot to a method that produces replenishable hyperpolarization. So that is not multi-shot, multi-scan. And so the three questions are, first, starting from the state of the art, how is the state of the art today? What are the kind of performances that we can obtain? And we'll see that dissolution DNP has become pretty efficient, can polarize fast to very high level with good repeatability, but there is still some very strong bottlenecks. And then I want to focus on what's changing now. So today there are some developments that I think are quite interesting. It's not so much on the DNP side, but it's more on the dissolution side. And that's, I think, where the bottlenecks are. So yeah, despite the name of the ZOOMinar, which is solid state NMR DNP, I will focus more on the liquid, or let's say from solid to liquid step. And finally, I really want to try to convince you that with the recent developments, there is maybe today an opportunity to make dissolution DNP become something that is multi-scan, that is replenishable. Okay, so we care about sensitivity, and in NMR, we often try to increase the sensitivity by investing in cryoprobes, sometimes very high field, of course, for resolution, but sometimes also only for sensitivity. There are some people who come to us at the CRMN in Lyon who want to do high fields only for higher sensitivity. And so sometimes there's a good answer to that, which is dissolution DNP, and that can boost the sensitivity by 10,000, even 100,000, depending on the field where you drop your sample at the end. So this is sometimes a very good solution. It's been shown to be very successful in MRI with like very impressive applications in metabolic imaging for cancer diagnosis. I think you all know this example where they have injected pyruvate and being able to observe the conversion into lactate in the prostate cancer region. And this is nice. It's a single shot method. So you inject the hyperpolarized media once, and then you can follow it in vivo, and you don't need multi-shot. Okay, but this is the main application of dissolution DNP, which is MRI. But so today we want to focus on NMR spectroscopy. So what about the NMR? And I mean, there are several applications that have been demonstrated by Hilty, Friedman, Giraudot, and I must forget many of them. But I mean, we must now come to the conclusion that the 10,000-fold enhancement is very often incompatible. And it is incompatible with actually the vast majority of the NMR experiments, the routine NMR experiments. And why is it so? It's mainly because the hyperpolarization that is created, that is transferred to the liquid state spectrometer is ephemeral. So it fades away within 10 seconds, sometimes a minute at most. And most of the NMR experiments, I mean, all of the NMR experiments that are multi-scan, do phase cycling, coherent selection, multidimensional. So you want to have 10, 100, 1,000 scans. And it's very difficult to make it really compatible with the single shot character of dissolution DNP. And it has been done, of course. So Lucio Friedman has demonstrated that you can couple it with what we call the ultra-fast 2D NMR. And it has been also done by us in collaboration with Giraudot. And so for some systems, the ultra-fast version is satisfying, but we must also admit that it also decreased the sensitivity compared to a multi scan 2D experiments, and sometimes it can also hamper the resolution, and sometimes you cannot excite the whole spectrum. So there are also some limitations that are inherent to ultrafast 2D, and it's not widespread. So what we would really like is to be able to repolarize the sample on and and have a multi-shot approach that is really fully compatible with the majority of the NMR experiments. And so the problem is that with the dissolution DNP method, we cannot just take the sample back in the polarizer and repolarize it. First, because it takes 20 minutes to an hour, depending on how you polarize, but also because when you do the dissolution, it's not only a dissolution, it's actually a destruction. You dilute the sample by 10, 100-fold, and you contaminate it because you have glazing agent, and you have radicals, so it cannot be just repolarized, and you have to find a way to avoid this dilution and this contamination. The problem is today we really need this dilution. We have to do it for the following reason, is that when you do your polarization, you use the radicals and you mix the radicals together with your molecule of interest. And the way we do it is very often we try to have a homogeneous mixing. So we put the radicals in solution together with the molecules, and we add some glycerol, and so that when we freeze the sample, it will form a glass, a statistical distribution of the radicals, and so it doesn't crystallize, and the radicals are very in close proximity to the nuclear spin, so that DNP works pretty well. That's what we've been doing for years, for decades. And then you shine the microwave. In our case, we are at 1.5 Kelvin, 7 Tesla, and we get polarization close to 50% for carbon, 80% for protons. It works really well. But the problem is that when you stop the microwaves and you warm up the sample, you start to have paramagnetic relaxation. And this becomes extremely intense if you warm up the sample close to the melting point. It becomes also extremely intense if you want to take out the sample of the machine. So if you want to go to low field, the interaction with the electrons become really strong. At low fields, you start to have overlap between the NMR line and the electron that has a very broad line. You have instantaneous or millisecond relaxation, and this is killing your hyperpolarization. So the trick, and it's the great invention of dissolution DNP, is to melt the sample in the polarizer. But while you melt the sample, you also dilute the sample by 10 to 100-fold, so that the electrons go far from the nuclear spins. The paramagnetic relaxation is very much quenched, decreased, and you can preserve the polarization during the transfer. And that's the reason why it works. But that's also the curse that today makes it impossible to just recycle hyperpolarization. So just to put that into context, I show you a little video of that shows how we perform the experiment. So we load the sample in this sample cup in the sample stick that is then inserted directly into the helium bath of our polarizer. Here it's a Bruker prototype machine that operates at 7 Tesla and 1.5 Kelvin. And once the sample is inserted, it freezes at 4 Kelvin. We close the sample and we can pump down to about a millibar to reach a temperature that is close to a Kelvin. And then the microwaves turned on, we immediately see the signals build up for protons, and you can also do CP on carbon. And after a few minutes, once it's polarized, we insert another stick, which is this dissolution stick. We couple this with our transfer system. It's a set of valves and tubings. And then we lift the sample up a little bit over the helium bath. We couple it and we press the button, and then the transfer is done automatically with hot water. So the sample is dissolved, diluted, and transferred through the magnetic lines, either solenoids or magnetic tunnels with permanent magnets. It goes in this valve that is also encapsulated in permanent magnet plates, so that the field is sustained everywhere and we avoid some of the very low field relaxation mechanisms. And then the solution comes in the tube. It takes about 1.5 seconds for the whole transfer, and it's once injected, we get this nice spectra with typically 50% absolute C13 polarization in the liquid state. Now it has become really routine and repeatable. We have this really high polarization with a very good resolution that, I mean, most of the time really match the standards of liquid state NMR, so below Hertz line widths. So just to go through the hardware, you may know the Hypersense that was initially developed by Oxford Instruments, and then SpinLab developed, GE developed the SpinLab polarizer, which is now cryo-free and has multiple samples. And more recently, Bruker has embarked in the development of a prototype machine that will become commercial soon. There's a new version in preparation that was announced at the HIT 21 meeting by Jim Kemp from Bruker. So the new version will be cryo-free also. And it will feature all the things that we have developed with microwave gating, modulation, CP, and various nuclear spins. But there are also many other setups that were home built. And for example, I can cite the one that we built with Morgan Sellier, Geoffrey Donhausen, and Baudin. Also the one from Lloyd Lumata, Matthias Ernst, and Arnaud Comment, and also the polarizer from Jan Henrik and Jarl Larsen, which is now a commercial machine with his company Polarize. So there are many setups. And now if we look at what's the kind of performances that we get, what are the kind of the best performances that we get, if we implement the frequency modulation and the cross polarization that we developed in Lausanne with Geoffrey Bodenhausen. And we also implement the microwave gating. This is a little trick that allows to improve the cross-polarization performances. It simply consists in switching off the microwaves before doing the CP, which in our condition leads to the relaxation of the electrons back to a polarization close to unity, and therefore no paramagnetic relaxations anymore. If we do that, we get a very nice CP efficiency, and therefore, putting all this together, we get between 50 and 60% polarization on carbon-13 in a few minutes. And here you see one of the best examples where we get a build-up time of about 3 minutes, up to 60%. Now the routine is more 50% polarization on a very like reproducible basis now. And once we get this polarization, we perform the dissolution. And with the system that has been developed recently in our laboratory, which is really close from what Lucio Friedman has developed in the past and Christian Hilty, it involves some fast valves. We can transfer and inject very fast. So solution travels at 4 meters per second, and it's injected within a 10 microliter precision. And then we get very nice spectra then. So you see here a 50% liquid state carbon polarization with line widths that rapidly reaches below a Hertz. So that's now the kind of state-of-the-art performances that we get on a routine basis. Just to show you the dissolution system is very reproducible, very repeatable now. So when we prepare the sample, we of course weight the sample with some precision of 0.3%, and then we obtain a carbon-13 polarization in the solid state with a precision that is 1.6%, which is, I believe, limited by the sensitivity. So it's more noise than real precision variation. And then during the dissolution, the timing to fill the loop and transfer is extremely precise because it's taken, it's made with optical sensors and automated valves. So at the end, we get a very reproducible transfer time. And so at the time of arrival, what we see is that there is some variation in signal amplitude because of changes in concentration, because of changes in polarization, which is not super good. But if we use an internal reference and we normalize with the internal reference, that we know the concentration. Today, we typically get variation coefficient that are close to 1%. So, for example, on the acetate, 0.8%. So despite all the manual steps and this dissolution and transfer, at the end, we get this 50K enhancement and we get a repeatability that is typically 1%. So it's very, very good, I would say, and it would really enable to be competitive for many NMR applications. But it's today really far from being a routine method to use dissolution DMP, because there are still some great limitations which are not really related to the DMP performance itself, but more to the fact that the sample is just destroyed and also is ephemeral. This polarization is ephemeral. So the second point I want to talk about now is about what is changing today. What are the things that have emerged that may allow to them reconsider the way we do dissolution DMP. And it's mainly about dissolution, contamination, and dilution. So as we said, I mean, because it's destructive, because it dilutes the sample, it's a great bottleneck for all the applications, because you cannot just make it multi-scan. But I think there are three things or three beliefs that today are changing. And the first one is the fact that we've been thinking for a very long time that we need to mix the radicals and to have a close proximity of the radicals with the nuclear spin. And this is not true. And we've started to use matrices, porous matrices, instead of homogeneous frozen glass. A long time ago, it was in 2014. We started to use silica matrices with the radicals at the surface. And so what we've been doing during 4 years, I think, was, I mean, we were doing it really wrong. Because what we have been trying to do with these matrices is to mimic as best as possible the distribution of the radicals in a frozen glassy matrix. So we started with SBA 15, which is with linear pores. Then we went to SBA 16 with cubic pores. And then we went to a non-structured material, which we call HYPSO 2, 3, and 5. And with the HYPSO 5, because the radicals are really distributed randomly, and the pores are very small, it really mimics the distribution of the radicals in solution, in the frozen solution. And because of that, we were getting really very good enhancement. And that way we managed to have proton polarization that was really close to what we would get in the solution. But on the other side, what we also tried to do is to make a very bad matrix and to try to not have a very good distribution of the radicals. And one way to do that is to make a powder out of your material instead of solubilizing the material in a solvent. So we would make a fine powder. When I say fine, it's typically 100 nanometer to a micrometer. And then we would impregnate this with a non-solvent. So instead of water or pyruvate, we would use toluene, THF. And the radical would be tempo with a ring tempo benzoate so that it would not get mixed up with the particles. So at the end, we would get these particles impregnated with the DNP juice, which was a pretty bad juice with toluene and THF. And this approach, luckily, also works. So you can polarize the juice, and thanks to proton spin diffusion, if you have 10% of protons in your water or in your solvent, then you end up observing a fast spin diffusion to the core of the particles, and you can polarize protons efficiently and then do the cross polarization as we had developed previously at this temperature and field. And what you would see is that the polarization takes a lot of time to build up, but it builds up in the micro powder. And once it's built up, you can also apply cross polarization steps. Of course, it's less efficient, it's slower than the DNP juice because the particles are big. But it works, so we realize that we can polarize with pretty heterogeneous sample formulations, which maybe was not really new because this is something that I think you guys from solid state NMR know well from a long time Griffin had shown that you could polarize some fibrils also that had like 100 nanometer typical diameter. So, but in our condition, it worked well. And the big surprise at that time was that if we would polarize a sample as a powder, then when we would switch off the microwave and warm up the crust to 4 Kelvin, so to standard liquid helium, we would observe extremely long relaxation times. So instead of a few minutes with the radicals mixed, here we would observe typically hours or tens of hours. In this case, it was 37 hours for pyruvate. So because the radicals were so much separated, the lifetimes would become so long on the carbon-13. And this enabled us to do the first proof of concept experiment of transport. And that was the second belief that was really destroyed, is that there's no need to dissolve the sample inside the polarizer. You could actually take out the sample slowly by hand, bring it in your helium dewar with some permanent magnets, and it would stay there for hours or overnight, and still after that retain some pretty big enhancement. And so that was the first proof of concept experiment that transporting hyperpolarization is actually possible. And you don't have to dissolve it on site in the polarizer next to your MRI machine. And then we pushed this concept further. We thought of making some matrices that would be suitable for this concept of transport. So we designed some porous polymer, which are epoxy resins that contain the radical, not on the surface like the silica, but inside the bulk. So the radicals are really embedded in the walls of the materials. And so when you polarize the material first, so you polarize the polymer, and then it diffuses to the solution that you have impregnated in the pores. And this turned out to be a very simple approach for preparing a sample, because you can synthesize the powder as a monolith or as a fine powder if you grind it. And then you just take your solution with whatever molecules you have inside, or mixtures of complex mixtures, and you can just put the solution on top of your powder and close the Eppendorf, and just by mixing by hand, you would get in the pore and you have the material impregnated. So the sample preparation becomes somehow universal for whatever sample that you want to polarize. This was very, very, very nice trick. And then when you do the DNP, so the HYPOP, as we call it, the porous polymer polarizes pretty well. And then whatever is in the pores would polarize in the frozen state, thanks to efficient spin diffusion over 100 nanometer or more, depending on the size of the pores. And so in this other experiment, we demonstrated that you could polarize C13 to 20-25% within minutes, tens of minutes, using all the usual DNP and CP that we had implemented before. And in the same way that on the particles we had long lifetimes, we could also observe very long lifetime on frozen molecules, typically hours to 12 hours for some molecule. Here, urea shows 5.7 hours when it's frozen and impregnated in the HYPOP at 4 Kelvin. So this showed us how actually we can easily take out the sample. It can survive for a long time, even outside of the polarizer. I must mention also another experiment from Benno Meyer that was demonstrated in 2019, which is the bullet DNP, where he also showed that you could take out the sample and dissolve the sample outside of the polarizer. So in this case, it doesn't dilute the sample as much as people do in dissolution DNP, but there's still a significant dilution factor. But it shows that you can, even with the electrons mixed, you can actually take the sample out if you go fast enough. And in his case, when I say fast, I think it's something like 10, 20 milliseconds for the transfer through a magnetic line. So it has to be really super fast. Now, the natural things to think about would be to combine this bullet DNP with the HYPOP, with the impregnated matrices, and that would enable to better preserve the polarization during the transfer, and maybe not need to go that fast. It could be a slow bullet, like a slow bullet would do it, because we do it by hand and it works. So that's not done yet, but that's really something we'd like to do with Beno. And the last thing is about dilution. So we can separate the radicals, we can take the sample out, and now the next thing is, can we melt without dilution? And if this is possible, it would enable to maybe repolarize the sample. Okay, so this is actually not really new idea. It has been already demonstrated in the past by Bob Griffin. It was long ago, it was in 2006, so it was really a visionary experiment. And it was also shown more recently by Kemgens. What they have shown is that if you have a sample that contains the radicals, and if you melt it fast enough, again, it has to be really fast, it's 100 milliseconds or so. If you melt it fast enough, you can actually preserve the polarization pretty well. It has to be really fast, so it has to be done with laser, IR laser in the case of Bob, or very tiny samples in capillary with hot copper in contact with the capillary. And so this is actually working. You can melt the sample without dissolution and still preserve part of the polarization. Okay, so of course, next, what would be really great is if we could do this melting in a way that is more smooth, that is more extreme, I would say, and get rid of the radicals that are in the solution, and that leads them to paramagnetic relaxation and eventually also line broadening. So therefore, I'm coming to the last point, which is replenishable hyperpolarization. If we look at what I've shown, can we think of a way to make hyperpolarization multi-scan replenishable easily? And so I'm going to stick on the materials that we are using now, which are the HYPOP materials, and that we can either provide as a monolith or as a powder if we grind it. And the way we use it today is we impregnate it, and then we polarize, and when we then dissolve, we filter it. So it's not an easy task to filter it nicely, but the way it is done is that it is filtered outside of the polarizer, in line in the fluid path that goes to the NMR spectrometer. So we use a filter that is in line, and the solution by diffusion escapes the powder and is transferred almost quantitatively to the NMR spectrometer. Okay, so the next step, the next idea that now seems really obvious is the concept that I call hyperpolarization flow, HYPFlow. And the idea would be to perform DMP in the matrix, where we can get a nice boost in sensitivity. And then instead of doing the dissolution as we do it usually, to have a melt, which would not need to be super rapid. Why? Because the radicals are not in contact with the molecules of interest. And this would give us more time to do the melting in a smooth way, a more gentle way. It would allow to melt and then extract the sample in a way that is pure. So without the contaminants, without the glycerol or the ethanol or the radicals, and without dilution. And if this is possible, it might also be possible to repolarize the sample because it has been unchanged, it's preserved. To recirculate the sample, refreeze it, and repolarize it. So the idea is to polarize the sample in the matrices in some DNP conditions that are advantageous, and then push the sample with liquid pump to the NMR spectrometer, which would be a nearby benchtop spectrometer, for example, at the beginning, and then to recirculate the sample on and on for hopefully 10, 100,000 times, for as much as the multi-dimensional NMR needs. Okay, and this is, I think, really possible today, and it's timely because we have these matrices that allow to nicely separate the radicals from the molecule and still polarize efficiently. We have the DNP and CP implemented, and we have now full control of the dissolution, transfer, injection in a way that is very well controlled. So now I want to show you two things that may support this. The first thing is about liquid state relaxation. When we melt the sample in the matrix, because the radicals are in the polymer, the relaxation times in the liquid state remain relatively long. So they remain, for example, in the case of acetate, of about 3 seconds. But then if we decide to remove the radicals at the surface of the pores and only leave the radicals in the bulk of the material, DNP is well preserved because the polarization is generated inside and will flow through spin diffusion in the solid state. So in the solid state, it's not a problem to remove the surface radicals. But in the liquid state, because there are no more radicals at the surface, the relaxation in the liquid state goes back almost to the native relaxation, because it does not see the radicals anymore. So we get long relaxation times in the matrix where the polarization has been done in a rapid manner. And that's, I think, a great advantage to have the separation between the radicals and the molecules for the melt precisely and for the liquid state. And the last thing I want to show you is some preliminary result that we have been acquiring at 100 Kelvin. So showing that we can do DNP at 100 Kelvin with such kind of matrices, and that the polarization build up typically in a matter of a second, 3-5 seconds at 100 Kelvin. And that might be a sweet spot to do the experiment, because melting at 100 Kelvin is much more easier than melting at 1 Kelvin. Of course, the enhancements are lower, but it makes it easier to freeze and melt, that, as it has been shown by Griffin and Kengans. So I wanted to show you all these developments and open it with this idea that might be possible in the future. At least we'd like to work on this in the future, if possible, which is to make hyperpolarization replenishable and pure and compatible and truly compatible with NMR, with routine NMR, with multi-scan NMR, multidimensional NMR, because we think this is one of the most important bottlenecks today in dissolution DNP. I mean, everything has been done on the solid side, DNP side, but I think there's more to do now on this melting and dissolution side. That is the end. So I finally want to acknowledge the team in Lyon, people that are now in the team, the people who left the team recently, Samuel Cousin, Stuart, Elliot. The persons that have been working on this are mainly Olivier Cala, Quentin Stern, Theo Eldahay, who developed the matrices, and we also have some new people who recently joined the lab. I want to thank the entities, the Lyon University, the CNRS, the ENS, the funding, our colleagues from CPE for the materials, and people from Bruker who support this project and this idea. And I want to thank you very much for your attention. I'm open for a question now.
Okay, really nice talk, Sami. You've made a huge amount of progress for over the, I mean, the dissolution DNP has really changed really quite a lot. I mean, it used to take, hours to polarize a sample, right? And now you can do it in a few minutes or so. So there are actually a couple of questions here already. From an anonymous attendee, thank you for the insightful presentation. I didn't understand how the dissolution inside the polarizer helps to maintain the polarization for longer duration. And can you make a comparison between dissolution DNP and bullet DNP? In principle, which technique helps to maintain polarization? So that's a couple of questions, all right?
Okay, so the fact that we can maintain the polarization for longer duration has nothing to do with actually the melting or the bullet. It's really the sample formulation itself that allows to maintain the polarization for longer. And that's done through this phase separation between the radicals and the molecules of interest. That's really the key to have a long lifetime. And then whether you use the bullet or you do the dissolution in or out, I think the fact that it's maintained for a longer time is really defined by this sample formulation.
Okay, the next question then, in NV-DNP, getting the polarization outside the crystal, it's, I guess, nitrogen and vacancy DNP, outside the crystal is a big issue. Why is this not a problem in your approach? And should there be some, go ahead.
Yeah, I mean, that's clearly the main problem with NV is that you can polarize your carbon efficiently in the NV and it's really hard to get it out. Because carbon-13 spin diffusion is just nothing, it's so inefficient. The reason why our approach works really well is that we polarize protons, and protons, they are so abundant, the couplings are so stronger, and the spin diffusion, it's 1,000 times more efficient than for carbon. So when we polarize in the material, the polarization escapes really fast. Whereas if we would polarize carbon directly in the materials, as it is done in NV, it would not work, just like the way it doesn't work efficiently with NV, because carbon-13 do not have this ability to spin diffuse fast. And the trick that we use is the CP, so we polarize protons, we let it diffuse everywhere in the solvent, and then we cross-polarize to the nuclear spin that we're interested in. So it's carbon, but we also did it on nitrogen, it can be done on lithium, on phosphorus, whatever. But the trick is really this indirect polarization pathway through proton spin, which allow to get out and to go everywhere.
Should there be some weak affinity from polarization to diffuse, from power to the target molecule? I'm not sure. That's the second part of the question. Should there be some weak affinity between polarization diffusion of, I don't know what's power to the target. I don't understand that. Anyway, maybe you do.
Maybe the question is about the chemical affinity with the molecules in the matrix. Actually, no, the molecules that we impregnate, for aqueous solution, we use epoxy, which is hydrophobic. So we try to not have strong interaction between the molecules and the matrix, but rather have the molecules just disperse in the solution that is frozen in the pores. And the spin diffusion is active over the whole length of the pores. I mean, right now we use pores between 100 nanometer and 1 micrometer. So, I mean, the molecule doesn't need to have any affinity with the pore. It can be in the bulk of this frozen solution, and it will eventually polarize after some time.
Okay. And Danella asked, how would DNP-based replenishable polarization for liquid state NMR compared with pH2-based Sabra?
Yeah. So it would you would compare first, it's more complicated than Sabre. Sabre is amazing and it's very simple. I think the great advantage that we would have is that when you are frozen and you polarize your solvent and then you do your CP, eventually, the spin diffusion goes everywhere. So you polarize all the molecules equally on protons. Then if you do CP, you will polarize all the molecules equally on another nuclear spin. And I think that's the great advantage, is the generality, is whatever we put in the solution, polarize equally. Then during the melting, the relaxation time might be different, so we have different losses during transfer. So that's one thing, but at least we start with an equal polarization before melting, and that's really great because it's very general. And to my knowledge, with Sabre, one of the problems is that it's more molecule specific. So you have amazing efficiency on some specific molecules, but not on a complete mixture of different molecules. I might be wrong, but I think that's the main difference, is this generality.
And Adam G says, nice talk, Sami. Do you see any difference between the solid state C13 T1 when using a CP buildup compared with direct C13 polarization?
Wow. So the T1 that you observe after CP in the matrices is typically between 1 hour and 12 hours. Because the carbons do not see the radicals, and because it's very much, the relaxation is very much diffusion limited. And so this is a good question, but I cannot really answer because we never tried to do direct DNP in the matrices. I think it would be very comparable, probably. It would also take hours, but since we have this cross-polarization available, it's so easy to boost it. So we don't even bother doing the direct carbon polarization. But say if you don't have CP, I would assume that it would work, and it would probably take as much time as it takes to relax. So it could be tried.
So a final question from Jeffrey. If you do not separate the hyperpolarized sample from the HYPOP polymer, does the susceptibility of the HYPOP prevent you from observing a high resolution spectrum of the trapped solution?
Yes, that's for sure. So that's for sure. I mean, except if you are at very low field. For example, we sometimes do some relaxation studies in the HYPOP in a benchtop spectrometer that susceptibility effect is not so strong. But you would certainly, I mean, it would certainly be a mess if you would do that at 500 or 600 megahertz. So that would be a problem. And that's the reason why in the approach that I propose to develop now is there is a separation between the DNP spot with the matrix that stays in place as a monolith and the detection spot where the solution is flown without the matrix. But if you do not worry too much about resolution, I mean, it's in principle possible to melt and observe in the matrix, and we have done it. We have studied relaxation in the liquid state in the matrix, but high resolution at high field would certainly be a problem. Jeffrey, that's right.
Okay, Kong, do you have questions?
Oh yeah, just a quick one. I'm just curious, like how do you see the comparison between your technique with other techniques, like for example, undercouples has this UV induced radical, and in Japan they have this photo excited triple state. I mean, these principles can be, I mean, their techniques can be also be made into a replenishable system as well, if I understood correctly. And do you see how can your system compete with them or compare on their advantages, disadvantages of each technique?
So you want to compare the DNP with radicals compared to DNP with photoexcited triplet state or with UV radicals?
Yeah, exactly. I mean, in terms of replenishable system.
Yeah. So, I mean, with UV radicals, the problem is that if you want to regenerate the UV radicals, it takes time. It takes actually a lot of time. It has to be done like in a low temperature environment with high power UV. So, I mean, it is an extra step. It's more complicated than just impregnating the matrix. The other problem is that with UV radicals, you have to generate a certain amount of radicals in your matrix, in your frozen sample. And for that, you need to have a certain sample formulation. So for each molecule that you want to polarize or each mixture, you have to rethink the sample formulation. It's not universal, but I mean, it could work. That's the main thing. I think the matrix makes it incredibly easy. Once you have synthesized the matrix, it's robust, it's epoxy, so you can just impregnate it. With the triplets, then it's very attractive. If you could replace the radicals in the matrix with triplet state, with pentasane, that would be fantastic. Then you would combine this approach with the triplet DNP. And therefore, you could do DNP at 100 Kelvin, but at the same time, generate triplet state that are polarized and get not 100 or 1,000 enhancement, but 10,000 or more at 100 Kelvin. And that's very, very attractive. Actually, there is one paper from I think it's Nobuhiro Yanai in Japan, who showed that it could use triplet state embedded in some MOFs, and that seems to work. So it's I think something that can be thought about. MOFs are maybe less robust than epoxy, but I mean it's certainly something that is very attractive to have combined. Porous media, flow, DNP combined with triplets. Yeah, that would be a dream. Yeah.
And just a quick question, like for your porous media, I mean, what is the pore size do you think will be so suitable for this technique so that you can get out the samples quickly and yet you have a good contact with your sample and your reticles, roughly?
Yes. Yeah. So at the beginning of the project, I was worried about the pore size. I was thinking small pores would make it really hard to have the solution escape. And with the HYPSO that have a pore of 5 nanometer, I was really surprised that when you come with an excess of water or you flow water on your sample, when it melts, it just diffuses really fast in the pores and it comes out. And actually, that's not the main issue. The main issue is relaxation. So we need a certain pore size to enable a certain relaxation time. If it's too small, it relaxes too fast. It's like a frozen solution. And if it's big enough, the relaxation becomes dominated by diffusion, and therefore the melting can be done slowly. There's no rush for melting anymore. Then comes the other limitation, which is if it's too big, it takes too much time to polarize. And right now, the sweet spot that we have found is about 100 nanometer, which is exactly the typical size of samples that Bob polarized in solid state DNP 15 years ago. I don't know if that's not 15, but yeah, maybe 10 years ago on the amyloid fibril experiment. So this seems like very good because it diffuses within seconds. You can polarize it at 100 Kelvin, and then the relaxation is dominated by diffusion. Therefore, you can melt slowly. I mean, when I say slowly, it's a second, it's not a minute, but you don't have to rush.
Right. Thanks for the magic number, 100 nanometers. Bob, is that the size of the GNQQNY heptapeptide?
They went from about 100 to 1,000.
Yeah. Okay.
I mean, so sorry, angstroms. Yeah, 100 nanometers. Okay.
Yeah. So that's the magic number.
Yeah. So there's one final question here is, what do you think about adiabatic transitions between spin states when a polarized sample is moved back and forth between two different magnetic fields? Does this distort the spectrum?
Yes. I mean, this has been a struggle, for us. So I used to do dissolution DNP in Lausanne with non-shielded magnets, and when we arrived in Lyon, we had all these nice ultra-shield magnets, and we started to lose the polarization. Not only distort the spectra, but lose the polarization because of the transition that would happen at very low field. So yes, it's a great issue. It can distort the spectra, but you can also just kill your polarization if you go through low field in now a non-adiabatic way. Especially if you go up tens of micro Tesla or so. So yeah, it's a problem and it has to be taken care of. And the way we do it right now is by using these magnetic lines. So with the permanent magnets, we have a field of about 0.7 to 0.9 Tesla. And with the solenoids, we pulse current and we get fields that are typically between 50 and between 3 and 5 millitesla, which is not great, but it's enough to preserve the line shapes and the polarization.
Okay, well, I think that answers all the questions, at least that have been posed so far. Of course, people are welcome to talk to Thomas and to Sami offline today, but I think Kong and I would really like to thank both of them for really beautiful talks today. Wonderful new spectroscopy at 1.2 gigahertz and 0.5 millimeter rotors, and with unusual carbon proton shifts in water, as well as some really beautiful new dissolution techniques that Sami told us about in some detail. And Kong, do you want to announce the next speakers in 2 weeks from today on the 15th?
Yeah, sure. So 2 weeks from today, 15th of February, we will be hosting Christophe Corpore from ETH. I mean, you have already heard some of it from Sami's talk, and also Thomas also has some of it. And also, the second speaker will be Daphna Shimon from Hebrew University of Jerusalem. So who will probably tell us about DMP on NV centers. Yep.
Right.
Yeah.
Okay, so again, Thomas, thank you very, very much. And Sami, thank you very, very much again for beautiful talks today. And we hope to see everyone again in a couple of weeks' time. All right.
Thank you. Take care.
Bye. Bye.
Bye-bye.
I think.
Bye.